This program, SHOWSPEC, demonstrates what a spectrogram is and how it is created. Let's start with a simple clip of speech and play it.
She sells seashells.
She sells seashells. This left panel shows a time representation of the entire sound. This particular sound takes about 2 seconds from beginning to end. The cyan bar here highlights about 40 milliseconds of the sound, which is shown expanded on this right panel. Now, speech consists of a bunch of phonemes, vowels, and consonants that are strung together in a time sequence. Here's a little piece of the consonant sh from she. Let's play it. You can point out that its time representation on the right panel here looks very noisy. And here is the E from she. And here you can point out that its time representation seems much more regular and periodic. The upper panel shows the spectrum of the highlighted portion of the sound in this lower right panel. What's displayed is the magnitude of the spectrum on a decibel scale versus frequency on a linear scale. You can use the cursor to point out that the spectral energy of E is very characteristic of the spectrum of vowels. The spectrum has spikes of energy at multiples of the pitch period and has most of its energy below about 3 kilohertz. Here's the sh from she again. The spectrum of this consonant doesn't have a lot of structure. It has a broad peak about 3 kilohertz and very little energy below a kilohertz. You can now show that the spectrum of each little time slice changes from moment to moment. And ask the question, how do we come up with a simple pictorial representation that displays the magnitude of the spectrum as a function of both frequency and time? Let's take it in steps. First, let's color the spectrum. We use the familiar temperature-like color scheme, where red indicates the highest magnitude and blue the lowest. Next, let's make the display three-dimensional. So what we're plotting here is the magnitude of the spectrum on this axis as a function of both time on this axis and frequency on this axis. Each time slice here corresponds to a spectral slice here. Now we can put all the spectral slices together to form a solid 3D surface that represents the magnitude of the spectrum as a function of both time and frequency. Finally, recognize that we have a duplicate representation of magnitude, both as position on this axis and also in color, and we don't need both. So if we rotate the plot up, so we're looking at it from above, now we have a nice two-dimensional representation of spectral frequency versus time with magnitude encoded in color, and that's the spectrogram. The spectrogram clearly shows the variation of phonetic content of speech as a function of time. For example, here's the sh from she. It shows a broad peak about 3 kilohertz. Here's the E from she. And this has the very characteristic spectral structure of vowels. This program is one of a suite of programs that I have developed to explain DSP concepts to my students during lectures. There are now well over 24 programs covering many aspects of the material in the book, including complex exponentials and sinusoids, convolution, the DTFT, pole zero plots and their relation to frequency and impulse response, A to D and D to A conversion, including upsampling, downsampling, resampling, and aliasing, the design of many types of FIR filters and their application to the filtering of speech and other signals, the design of IIR filters, circular shift and convolution using the DFT, the discrete cosine transform, and the short-time Fourier transform. A selection of these programs is being made available to instructors who are currently adopting the book in their classrooms. For further information, please visit cambridge.org/Holton.